So welcome to the, I guess, on the agenda, second to last talk here on Thursday morning, UGM 2021. This is David Wade from Integral Engineering, and he's going to give us a talk about towards a scaled system of ingest, analysis, manipulation, and deployment of multiple high-end video codec streams with HPC and iRODS. Take it away, Dave.
Well, thank you to Dawn for organizing this. Thank you to Terrell and Jason for inviting me. Just a little bit about myself. Before coming to Integral, I worked for a company in San Diego, General Atomics. Many people do not know General Atomics was a founder of the San Diego Supercomputing Center. Dr. Regan Moore was on staff there. And when I came aboard, I worked to General Atomics. I worked on a software system for transparently moving data from disk to tape, so-called hierarchical storage management. Out of my work, General Atomics builds several types of what I call mobile agents, the best known of which is the Predator unmanned aeronautical vehicle. It's the one you read about in the newspaper that flies in Pakistan. People also should know it flies over California looking for forest fires and telling helicopter water dropping pilots where to get in. It's unmanned. It's flown by wire. Let me start. There are many, many, many video cameras in the world today. In London alone, 50,000 cameras in the city at least. That was a few years back. And many planes, cars, let's see, Humvee, Mars rover, satellites are all carrying cameras. Highly efficient video codec or high-end video codec is the standard from the ITU that allows these cameras to operate at 4K frames, 8K frames, 16K frames, and 32K frames. You're most familiar with 4K if you've watched a Blu-ray. And if you've watched a high definition, so-called 4K Blu-ray, you're looking at HEVC. Now, these various agents can carry sensors, and one of which would be a HEVC camera. That's not a real HEVC camera, but it's standing in for one. A radar is carried on the airplane, a LiDAR on a car, Mars, so on. So what we are talking about in this presentation, and this is kind of a scaled down, very quick overview of a system that can ingest various types of sensor data onto a mobile agent, store there, also transmit to a ground station somewhere. And on the ground station, what you want to do is you want to run in parallel lots of different, what I'm also calling agents, and these are software agents, that are going to analyze the video. Now, why? The HEVC on the Predator can be carried in a pod on the wing of the Predator. It can carry 3 pods, and this is a device called Gorgon Stare. Up here is a little cartoon of what it can do with one camera. There's, I don't know how many you count there, but it can carry up to 13 cameras per pod. It can carry 3 pods. So this plane in flight can carry 39 cameras. And those 39 cameras, of course, recording, streaming content, streaming HEVC video. But an issue in all of this is that the airplane is flown and communicates with the ground by what's called a KU band satellite link. And KU band is somewhere in this, but what the problem we will see is with this amount of camera and the amount of data that we're going to record, that data cannot be transmitted to the ground entirely in a basic mission of a 40-hour flight. What the idea of behind all of this is that we want to develop a system, sorry about that, that while we're recording on the plane, We are capturing this in a Lustre data cache, but we also want to apply some kind of filtering. So we need a system that brings the HEVC from the 39 cameras in streams, each coming from one camera, into what I would say what is a high performance computing cluster. And the head nodes are controlling IO nodes, and the IO nodes are passing this to Lustre, and iRODS is doing the data sharing. Why we want iRODS on the airplane is not just to facilitate all of this, but when the airplane lands and we maintain the Lustre system running or the data cache running, could be Ceph, we then have landing zones that we just hook up another system very much exactly like this, software-wise, and the data is seamlessly moved into our ground-based analytical engine. So we have the same software running on the plane as running on the ground, with the exception that on the plane, it's scaled down to those kinds of devices and those kinds of data retention that can fit on an airplane. This is about the size of a Learjet. It's simply a military Learjet. So to go further, the ground station, you see, looks exactly like what we're doing on the plane, but we have a further set of HPC visualizations. Now, the purpose of all of this and its reason is, it turns out that even the videos that are being piloted, because this plane also flies with a camera, when this data, the amount of it comes to the ground, at current times, nobody really does anything with it. They just watch it. But if you think about that, that is soon going to be not a optimal mechanism for understanding, because you're watching this video. Okay, I watch this video, I see this car approach this house. I know there are drug cartels in the house. I think you're hearing that I'm kind of repeating the plot of a Jack Ryan movie that came out many years ago. And you send a missile into the house and blow it up. But you simply assumed that this is your target. If you were flying over the ocean and looking for a periscope, doesn't matter how many cameras, it's very unlikely you'll be able to spot the periscope, but very likely that with pattern matching on the individual frames, you'll be able to do this. So again, what you take out of this is all different kinds of sensor data, but for us, our model is HEVC, gets ingested on the airplane. We can analyze it. We can pick frames out so that we just send down over the satellite link the frames we want. When it arrives at the ground, whether it's streaming to the ground over the satellite or when we land the aircraft, we move this into a visualization system. Now, here's what we're going to do. So in the background are these, mock video streams. There are many of them. There are tens, hundreds, thousands, 10,000 streams of HEVC that we wish to operate on. We wish this to be scalable. We can operate on one stream, or by adding more components, we can operate on hundreds, thousands, 10,000s. So the data management, as we scale it up, has to be scalable. One reason to choose iRODS for your data management, because it's proven geographically scalable, right? We don't necessarily keep all of these streams in one place, one ground station. We want to move between ground stations on different continents. Now, the analysis one-tail operations on incoming, outgoing, as well as cache capture. So with Lustre, Ceph, iRODS, we can move streams from our captured and our archival on the ground station, our archival set. We can move them into our device, and we can compare frame by frame with currently streaming or currently inputted data. This can be highly advantageous because we want to look for things in the video that we've already seen. So going further, the purpose of all of this is to support situational awareness. In a battlefield situation, for instance, the planes are there to support ground troops. But if the ground troops have their mobile agents and the planes, and they're all being mixed, where they can be aware of hostile intent in very immediate context, not down the road. Now, I've done a certain amount of computation here. We are talking about streaming at 96 frames per second, because it is 96 frames per second that would allow us to superimpose a virtual goggle-based system on top of the real video. And experience has now taught people using virtual reality systems that unless they are reading at 96 frames per second, people physically get ill. I mean, it sounds surprising, but if you actually are using virtual reality and you're only doing 24 frames, people have experienced nausea. If you add these all up, 4K frames, 96 frames per second, 40-hour flight time is an average flight time, one stream per camera, 39 cameras. You get an amount of pixels that converts at 3 bytes per pixel, because this is color mapped, to 6.46 terabytes for one 40-hour mission. Now, that's enough to fit on one solid state drive. But again, if it's broken up in Lustre, then Lustre agents can move it in parallel and we can get it off the airplane faster. However, why can't we get it off the airplane through the Ku band antenna? Because with this number of bits and this number of megabits per second that the Ku band is able to transmit at 40 hours, it would take us 146 hours of data transfer to get a 40-hour mission. So that's unlikely. Now, this is a schematic diagram of our chain of reasoning of how we're going to do this analysis. So we have this configurable sample of HEVC. Maybe we want to take every 1,000 frames. We're going to load this in an HDF5 struct. Now, HDF5 is a well-established in-core, or if you will, data containers. I'm not a container in the sense of the cloud, but this is a container that, like NetCDF, we can hold data in one bundle, and it has opaque structures. It can hold pixel maps, it can hold video, and it can hold a lot of metadata. Having wrapped this, ingested this in here, we then are going to pass these to the agent process that's doing our analysis. And we simply pass them in a pipeline. So we bring these in, and we may be bringing them in here. We're passing them here to do something. Maybe we're selecting frames. We pass them here, we're doing the comparison. Maybe here we're doing some pattern matching. Here we're doing some output. But what we will get is from various devices, including, again, our store on the ground station or on the plane, and Ceph is there and Lustre is there. DDN supports Lustre. I just threw that in, a little bit of support for them. But our multiple HEVC frames are streaming from deployed mobile agents and stored frames on those agents. Streams are being analyzed both on the agent mobile and across mobile agents by contact with what can be sent and received to the ground. When the mobile agents are homed, the data they carry can be landed via iRODS and moved off the mobile to the ground stationary system. So this is similar to the last slide, only this is to show that across all of these frames are agents that contain the HD5 video frames are kind of configurable. And they're configurable on the aircraft, on the ground station, such that we can choose different paths through these. I haven't shown the paths, but we could start and just do one HEVC on the airplane. There's a configuration step first to all of this, but then we start selecting frames and we do analysis on them. We might, from the Lustre file system, after configuration, select, do some analysis, and then we can store to any number of, first to Lustre, but then to any number of archival systems. We can pass the agent across multiple streams. We might want to do editing, cut and paste, and overlays. We might want to do selective retrieval. This represents the final pipeline end of the unit that, excuse me, the unit that we have chosen for our pipeline will be configurable. And when we're done with that unit, we want to close it, store it. We're already starting the next batch, but this just shows our first, our second use of iRODS, because when we in the pipeline, we want iRODS to be watching while we're loading this to Lustre. And if we need to get metadata, we can use iRODS to load it to Postgres. So Postgres can hold both the HDF5 and can hold the metadata for each one. And we collect metadata on all of these streams. So that's just a schematic. Now, what does a system like this is intended to look like? Well, this is just my schematic of what amounts to a standard HPC system with nodes that normally would be compute nodes. They are compute nodes, but they also act as ingest nodes, or we may divide them up, again, configurably. We have a Lustre file system for our data cache because it's fast and it's parallel, and we can bring the either the landed data, iRODS will move it, or the data that we can stream comes onto our ground station through some content delivery network. I've said Akamai, that's a worldwide network company, does worldwide networking. This could be any cloud, or this could be direct point to ground with a laser, something like that. So while we're doing the pipeline we discussed earlier, we're also choosing to save it all to Lustre, but then it can go out on an IO node. It can go back to another ground station. It can go even to another aircraft. It can go again to an archive. And here's a slide that simply overlays the cluster with the pipelines, tries to show you that we're doing many things on these nodes. We're ingesting, we're analyzing, we're storing. They are large nodes. They are fat in the sense of lots of RAM, processors, and so on. That about completes this part of the presentation. However, just for fun, do I have any time, Terrell?
You do. We've got, I don't know, we've got until 12 for us, but, you know, probably another 10 minutes maybe total.
That's fine.
Okay.
What I want to show you is, what do you do when you say analysis on video? So this is not HEVC. This is a public domain sample MP4. It's 14 seconds, and you can see that it's just a bunch of cows. Notice on the left here, I'm sorry, I should blow this up, I guess. You can see on the left here, the cows are coming from into the frame, walking forward in the frame. Okay, there they are. Let's iconize this again. Let's put it down. Now, okay, let me get to the Python system. Now, I've written some sample Python scripts, and we have one called video. Can you see that, everyone? We can
Yes.
We can apply our Python script called video to frame, and what we will do is we will load frames of the MP4 into this. So let's run that just to show you that what we see. So now I'm listing the creation of every new frame, and a frame in this sense is a JPEG file. So this takes a while to run, but it'll run pretty quickly. And then what we will see when we finally come to the end. So this is parsing the MP4. And now if we look back out at our var temp frames, we see all of these JPEG files. I haven't sized all of this, but basically we've taken every frame and we've divided it up. Now, there is an alternative that puts the frames back together, but I've also written this frames reversed to video.py. When I run that, it will put the JPEG files back into the order that I've chosen. And since that takes quite a while, what I'm going to do is try and load this to the reversed. Oh, let's see, I don't want to show that quite yet. But having already processed this, what we see is that now the cows are moving backwards. So this is just fun, but this is the type of operation. I don't see a big point to just reversing the frames, but the point is also, if I insert anything into this JPEG with the right right numbers, then I'm inserting frames into the movie I make. And again, we could do this with tens, hundreds, and thousands. So that really concludes my presentation. Let me just bring this back up.
So we do have one question. Thank you, Dave.
Okay.
Question
Well,
from.
I just wanted to show you
sorry.
on the last slide, here is the standard for HEVC. Here is a tool that you can download. It runs under Linux that will allow you to record, convert, and stream. Here's the iRODS group. General Atomics, the company I used to work for, makes the Predator. So here's information out there. So you had questions.
Yes. So first of all, thank you. That's great. I'm happy you could join us. One question from Matt at Soft Iron. It says, instead of luster, could this be Ceph on board the aircraft?
Absolutely. You'll note that I included Ceph here as one of the sources. It turns out that I have a very good friend that teaches at the University of California, Santa Cruz, who was an author of Ceph, and he's seen these. He was also a General Atomics person, but in this, let's see, how do I do this? What I've tried to establish here, the iRODS component of this does three things that I like very much. It allows me to create a landing zone where I can keep the data until the mobile agent stops and I'm ready to unload it, and then it helps me unload. The other thing it does, of course, is we've seen that it allows us to move that data off that platform. It also allows us to move data between Postgres, HTTP, AWS Lustre, NFS, CIFS, and Ceph. All of these things are a reasonable expectation for a analysis group to be using. The last thing I want to say about iRODS that I think is really great is that it mitigates what's called the namespace problem. So you have a namespace issue between POSIX on Lustre and NFS and Ceph, which is object store. But iRODS can be written to handle that transparently. You just write to the iRODS landing zone and it's moved wherever you want. So Matt, the answer is yes. I have looked at Ceph, haven't played with it extensively. The reason that Lustre is there is I want a caching file system. I want something that's parallelized and we go right into it. If I'm going to store the data long-term, I would say object store with Ceph. And then I would say to share that out to other ground stations of the world, iRODS would move from Ceph to HTTP, AWS, or NFS, CIFS. I mean, at one time, DDN was building what they called a web object store. They're no longer really supporting it, but it was basically HTTP on top of Ceph. I believe Dave Fellinger, you can talk to him. He worked on WAS. It was part of the larger picture. So again, are there any other questions?
There are. As a follow-up, it says where is Ceph currently exist in the workflow? Is it?
Ceph currently would be either, it would not be the immediate endpoint of where we're archiving. So right. Ceph, again, could run with Lustre on the aircraft. And this would be optimal because we could move things from Lustre to Ceph. And then when we land the plane, because remember, we can't get all the frames down, but when we land the plane, iRODS would just move from Ceph system to Ceph system. So right. Ceph would be on the airplane and on the ground station. We would move it into Ceph, but for the purpose of doing this, which we're doing in parallel, I would suggest that it would then be moved to Lustre. So each one of the compute nodes here would mount, a Lustre file. We would open one file on Lustre to contain the configurable number of frames of the video that we're storing. We would also have a file that contained the analysis results, but that might be in Postgres. We might, though, want modified frames to be stored. So again, Lustre for parallelism and Ceph for the archival storage.
Right. A question from Groningen says, how do you combine different sources? Do you use timestamps? Do you use metadata in iRODS for that?
The iRODS rapid ingest could be in use. Integral engineering actually has a highly scalable ingest engine that using, and it would run with iRODS as the rapid ingest, but the highly configurable can run on one node. And what we do is we pass Ethernet at a gigabit per second through InfiniBand, and we would modify or we would process each one of these at each interrupt using cores on the processor sets or cores on a GPU. So by doing this, we could get up to 200 individual sockets, if you will, in one Mellanox, InfiniBand card. We can add more to get more. And then these agents would also be MPI enabled, so we could move buffers from one stream to the next. So yes, iRODS has a place here as well. I didn't emphasize it, but the way that we get all this different data to ingest is that once it's in a buffer here, we pass it to one of these agents that will do some kind of conversion,
Right.
or will do some kind of understanding of what we've blocked out in HDF5, whether it belongs with similar content. So this was a framework, right? This whole system, which was originally called Voices for Video Optimized Interactive Computing Environment, is a way that people can get a handle on managing these quantities of data and reading them, if you will, with analytical tools. This could include machine learning. This could include TensorFlow.
Sure.
You could have that running, but we built a framework that can take lots of different sensor data and using these agents, match them up, and then between different similar, and even between similar and different, we can do different operations. And this would be configurable, right? So hope that answers your question.
I think it does. Pretty impressive. Thank you so much.
Well,
Happy to
again,
have
thank
you, and we'll do it again sometime.
Yeah, my name and contact information isn't on this, but I'll put up another, send another one of these to Dawn with it, so you can reach me. Thank you very much,
Sure.
everyone. Thanks for attending.
Appreciate it.